you can turn things back to me.
Thank you so much. I am pleased to welcome back Barry Bird from Junior University, and he will be discussing secure communications with quantum key distribution.
And here we go. How many of you have done anything to investigate the world of quantum computing? Who has done that?
I've been to a few of your in-person talks on quantum computing at
Cool.
Trends.
And you're actually coming back. That's it. That's encouraging. All right. What else? Anybody else? Yeah, I've been
worked with it too.
I'm sorry, say that again.
I'm sorry. I've also worked with quantum computing.
What?
I've done a couple of different prototypes using Qiskit. And
Okay.
Python.
All right, cool. How do you like Qiskit?
I think it's great. I use Qiskit with the IBM Q. I actually gave a presentation yesterday at the TCF conference.
There you go. Okay. So
yeah, I have a whole repo, a GitHub repo.
So I'm going to ask you, if I say something that's incorrect, then catch me afterward, not during the talk. Just don't, right?
As long as you don't talk about faster than light communication, I think we'll be okay.
I won't do that. I have 3 ways of answering questions. One of them is to answer honestly. Another is to say, I don't have time to talk about that. And the third is to make up an answer when I don't know the answer. And so if I do that third thing, then Corey, just, wink to me or do this or something like that, and don't mess things up for me. Okay, here we go. Primary objects, Oracle. There we go. Okay, good. All right, here we go. Quantum key distribution. That thing that you see, that's a picture of a quantum computer of one sort before it's dipped into a vat of supercooled helium. Is it hydrogen? Helium. It's got to get to a very cold temperature, 4 degrees Kelvin, something like that. And all the quantum computing, all of the processing power is at the very bottom of that thing where you see a little gold disc. The rest of it is just controls. So, and quantum computers in the world now, they're not very powerful, but this technology is developing. I think IBM said that it has about 100 qubits in a quantum computer, which compared to the millions of bits in the computer that's right in front of you right now, 100 qubits isn't much, but it's a darn good start. Things are moving along. And in fact, in the real world, some companies are getting ready to sell quantum key distribution services. Now, quantum key distribution, strictly speaking, is not quantum computing. It's not solving a problem by churning away qubits and coming up with an answer. But it is a way of making sure that communications between parties are secure. And it's a pretty effective way. I'm going to show you how it works. One of the sources that isn't listed on this slide is British Telecom. I very recently viewed a webinar in which British Telecom was announcing that they would actually be selling quantum computing, quantum key distribution services within the next year or so within Europe. And they're just getting ready to roll out. They've got almost all of the technology under control. There are a couple of orchestration things that they've got to do. But whereas solving real problems, actually churning out answers with quantum computing is years away, actually doing communications and doing secure communications with quantum computing is just on the horizon. We're going to be doing it soon, in a year, 2 years, it's there, it's practical, it's real, it's going to happen. So this, I hope you can see it, I hope you can read it, is one of the ways that we communicate securely. And I don't know if this is large enough for you to read. I'm going to pause for a minute and ask you if it's readable.
Yes.
Mike says yes. Do other people say yes? And you know, if you're not a Zoom fanatic, yeah, if you're not a Zoom fanatic, one of the things that you can do is you can, in the upper right corner of the Zoom screen, there's a little button that says view. If you click on that and go from gallery to speaker view, then you can see this slide much larger. But there are two kinds. Encryption means making a message unreadable so that it can get to its destination and there be decrypted so that it can be read by whoever it is we really want to read it. So how do you encrypt a message? Well, there are two ways class users of doing it. One of them is called public key encryption and the other is called private key encryption. This slide describes private key encryption. The idea with private key encryption is that you have to have a code that is used to encrypt the message and also to decrypt the message. And since both the sender and the receiver have to have that code has to be kept private. So let's take a look at this. Alice says, I'm sending you a very large private key that can be used for both encrypting the message and decrypting the message. And the very large key that Alice sends to Bob is, in this example, the number 2. Okay. 2 is not a very large number. But I used 2 in this example, and we're going to pretend that 2 is a large number just so that we can get this idea across. So let's say that 2 is this, instead of 2, that we've got this enormous number, and Alice makes it up at random, and she sends it to Bob. And Alice says, I'm going to multiply my message by that enormous number, 2. And she says to Bob, when you receive my encrypted message, you divide that message by this private key 2 so that you can see what it really says. Okay, so Alice says, hey, our private key is going to be 2. Only you and I know that. And Bob says, okay, I've got the number 2. And then Alice, in plain text, that is to say unencrypted text, says 4D77722E205, and that's the encoding that anybody could read of Mr. Watson, come here. So that's the message that Alice wants to send to Bob. But she doesn't want everybody to be able to read it in transit, so she multiplies that large number by 2. And then what she gets is 9AE blah, 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 which if you don't know the number 2, you can't make any sense of. So she sends that encrypted text to Bob, and then Bob gets that number 9AE45 blah, blah, blah. And since he knows that Alice got that number by multiplying by 2, Bob says, I'm just going to divide it by 2 and I'll get back 4D722, which I can readily, by international standards, well-known international standards, interpret as Mr. Watson, come here. Now, the flaw in this whole scheme, or a flaw in this whole scheme, is that there's a private key. The number 2 has to be kept secret between Alice and Bob. And that has to be communicated somehow. So if it has to be communicated, then the sending of that number 2 is as vulnerable as the sending of the original message, right? In a way, classical private key encryption is just kicking the can down the road. Instead of sending Mr. Watson, come here in plain text, you're sending it encrypted by a secret number, in this case, the number 2. But how secret can that number be if you have to send that in plain text? So that's classical private key encryption. Now, of course, in private key encryption, there are ways around that in classical private key encryption, but there's a quantum way that's really, really clever, and that's what we want to talk about. I'm going to pause for a minute and see if there are any questions, if I have any sense. Please stop me immediately, not by typing in the chat, because I don't look at that. Stop me immediately by unmuting yourself if you have any questions or any concerns at all. Is everybody good? I see absolutely no responses. So how are we doing? Am I making sense?
Yes.
I have a nod from Daniel. I have a yes from Bob. Everybody else?
Makes sense to me.
We're good?
Yep.
Okay.
Good.
Steve says yes. Neb says okay. Aaron says yes. Good. Okay. Private key encryption is just kicking the can down the road. Exchanging a private key has to be done somehow more securely. Before I march on, let me just mention that there's also this thing called public key encryption. Public key encryption is much more commonly used, as far as we know. But what does quantum computing have to say with public key encryption? Instead of helping encryption along when it comes to public key encryption, quantum computing potentially can break our current public key encryption standards. So there isn't terrific news there as far as quantum computing goes, but that's another talk entirely. Okay, how do we manage to communicate a number like 2 or a very much larger number that is going to be our key across a public network? Now, we have a slight advantage, and the slight advantage is that Alice and Bob can share a number, a very large number, without either of them having determined it in advance. When Alice wants to send a message to Bob, she knows what message she wants to send. She sends, Mr. Watson, come here, or I love you, or, you know, get out of your house immediately. I notice that there's a fire in your neighborhood, something like that. Alice knows what message she wants to send. So it originates with Alice and ends up with Bob. The advantage that we have with the key that we're going to exchange in advance is that key doesn't have to be any particular value that Alice knows in advance or that Bob knows in advance. They can sort of generate it in concert with one another. It's just an arbitrarily large number that I'm going to maybe multiply by the Mr. Watson, come here message. So the idea now is going to be to use quantum mechanics to have Alice and Bob in concert with one another generate the same number without actually communicating that number over a regular open network line. So let's talk for a moment about some quantum concepts. To do that, I'm going to switch to another slide. And now, here's the deal. In classical computing, you have 2 kinds of bits. You have a 0 and you have a 1, and that's the end of the story. Nice story, very simple, that's cool. In quantum computing, you have a 0 and you have a 1, and now I'm going to do something, you know, step aside Pixar. This animation is going to, you know, blow them away. Here's a 0. I'm going to click on this thing and There it goes. Never mind the little bit of code that's beside it. Oh, you know what? That 0, it isn't moving. It's just sitting and staying still. Okay, forget about it. My computer is not behaving today. That 0 is supposed to be blinking. And the reason it's supposed to be blinking is to indicate that we can only tell that a qubit is 0 by observing a bunch of them that are 0 that are supposed to be the same and saying those are all zeros. If we try to measure a qubit, one single qubit, to say it's 0, that qubit was 0, that's not going to work. Quantum mechanics doesn't work that way. So imagine that 0 that you see, the one that's kind of shaded, is blinking to indicate that what really 0 is in quantum computing is a whole stream of 0 qubits coming at us, and we measure them and they're all 0. Then there's this thing called 1, and there it goes. 1 is blinking for me. If we get 100 things that are supposed to be 1 coming at us, and we measure each one of them, and each one of them is 1, then we know that we're getting 1s sent to us. But in the qubit world, there's a lot of stuff between 0 and 1. There's superposition. And what superposition means, and now I'm going to click my final animation button and hope for the best. What superposition, oh no, that didn't happen. What superposition means, oops, here we go, one more time. Oh, come on, behave for me. Not doing it. Okay, here's what's supposed to happen. If I click that button 3, then a qubit in between the two, in between 0 and 1, is supposed to start flashing for you. And what that sort of means, how loosely you want to describe it, depends on the audience that you're talking to. I'm going to say this. There's such a thing as having a qubit in a 50-50 state, where half the time that you measure it, you get a 0, and half the time you measure it, you get a 1. And now the way I said that, I guess, was really imprecise. Let me put it this way. If there's a way of putting qubits in a certain state so that they're in superposition between 0 and 1, and if I get 100 of these qubits sent toward me in that half and half state, in exactly that half and half state, then chances are I measure the time I'll see 0 and half the time I'll see 1. So if you don't care about that probabilistic description that I just gave, think of it this way. I can put a qubit into a state so that it has a 50-50 chance of being measured as 0 versus 1. When I measure it, I'm always going to get 0 or 1. But whether I get 0 or 1 for a 50-50 qubit depends on probabilities. If you send 100 of these toward me, the ones that are in 50-50 state, then maybe 45 times I'll measure 0 and 55 times I'll measure 1, something like that. Anyway, it's half and half. Okay, let's march on and see what we've got here. There's this thing called the Hadamard operation. Corey, am I being sufficiently faithful to the discipline so far? Corey doesn't want to chime in. Okay, here we go. There's this operation called Hadamard, named after a French mathematician whose name was Hadamard. And you can Hadamard a qubit by hitting it with a laser or a microwave or something else. And when you Hadamard a 0 qubit, you get one of these 50-50 states. So if I start with a, let's say, it says bit here, but what I really mean is qubit. If I start with a qubit in the 0 state, or in the 1 state, if I Hadamard it, it goes one of these closed states. And if I Hadamard it again, it back into the 0 or 1 state. Now, what does this diagram mean? What this diagram means is if Alice does not Hadamard her qubit and Bob does not Hadamard what he receives from Alice, then the probability of his reading exactly what Alice sent is 100% 1. Similarly, if Alice starts with a 0 or a 1 at her end, and she Hadamards her qubit, putting it into this 50-50 state, and then at the other end, Bob Hadamards what he receives from Alice, then again, double Hadamarding just undoes the Hadamard operation. So it turns out that if Alice Hadamards a 0 or 1 bit, sends it to Bob, who then Hadamards what he receives, the probability of his reading her bit, the original bit accurately, is also 100%. If they either both don't Hadamard or they both do Hadamard, then Bob will accurately be able to read the 0 or 1 bit that Alice sent.
What
However,
does this physically assume? Like, what is this network? Is this a 100-foot wire, or like, can you make this concrete?
it depends on the technology for creating qubits, and there are about 4 of them right now. You can think of it as a laser light that's either polarized up and down or side to side, up and down for 0 and side to side for 1. And then you're sending it over an optical wire. You can think of it as what they call a trapped ion. There are many different ways of implementing this physically. And I'm not going to lie to you, I am not a physicist. I'm not well studied, well versed in that.
Okay, but like you can get a bit to a faraway destination
Absolutely.
still intact.
Yeah.
Okay.
Well, I mean, you can certainly, British Telecom has experimented with it in Europe. And, you know, they've sent it all the way across from Britain to whatever distance they've done, hundreds of miles,
Thanks.
thousands of miles. It's tricky. I'm not going to lie to you. Well, I might lie to you, but not now. If the bit isn't Hadamarded, then that's easy. You send just a 0 bit across the wire and a 0 bit ends up with Bob. Or you send a 1 bit across the wire and the 1 bit ends up with Bob. When you take a bit and you Hadamard it, you put it in this 50-50 state, those 50-50 states are delicate. They can decohere. Noise can easily disrupt that 50-50 state. So that's tricky, but it's apparently doable with today's technology. Okay? So once again, if Alice and Bob either both Hadamard or both don't Hadamard, that's the top 2 lines on this diagram, then Bob will accurately read what he gets from Alice. If on the other hand, one of them chooses to Hadamard and the other doesn't. So for instance, on the 3rd line here, Alice chooses to Hadamard, but Bob doesn't. Or on the 4th line, Alice does not Hadamard, but Bob does, then the chance of Bob reading accurately what Alice started with is 50-50. If on the very bottom line there, Alice decides to send a 0 to Bob, she doesn't Hadamard it, so it's a 0 all the way across that line until it hits Bob. Bob then Hadamards it. It puts it into a 50-50 state. Bob has half a chance of reading it accurately or not. And that ends up being good. Why does it end up being good?
Harry, on the slide,
Yeah.
what I find a little confusing, if once it goes through the first Hadamard, if it's in a 50-50 state, shouldn't the second Hadamard operation have a 50-50 chance of restoring the correct state?
That's the bizarre thing about Hadamard. It's an accurate inverse of itself. It undoes itself. It works.
Okay, it just seems strange that it would be unable, that it would be able to accurately undo something that only has a 50%.
Yeah, I think the best way for me to explain it is that in addition to putting these things in a 50-50 state, there's also some extra stuff going on there. So there are enough differences between different kinds of 50-50 states so that the Hadamard that Bob has can exploit those differences in order to recover the original bit that Alice sent. There's not just one way of being in a 50-50 state.
Okay, that helps.
Yeah, there's one way of being, there's a way of being in a 50-50 state so that you were originally a 0, and there's a way of being in a 50-50 state so that you were originally 1. And as a matter of fact, there are an infinite number of ways of being in a 50-50 state, but let's not go there. Hadamard, one way or another, undoes what it started with. Okay?
Okay, thanks.
All right, now I have to be aware of the time. And I promise myself whenever I start these things that I'm going to look and see when we finish. And I didn't do that. Can somebody, Ellie, are you still here? Can you, how far?
120.
What?
120.
Okay, all right. Let's see what we can do here.
Okay, so if you were trying to listen in to the message, couldn't you just use the Hadamard and not the Hadamard and then look at the two messages and see which one made sense?
Oh yeah, absolutely. That's why this is going to be a little bit more complicated than that. First of all, remember that we're just exchanging a key now. We're not exchanging. Well, okay, yeah. Let me march on. Okay. Yes, we don't want to just use this raw for quantum key distribution. Steve, okay?
Sure.
Okay, here we go. Here we go. Let's see what I've got here. Okay, so we've got Alice and we've got Bob and we've got possibly somebody in the middle who we'll call Eve because Eve would be an eavesdropper. So here's what we're going to do. I hope you can read this. You can?
Yep.
Alice makes up 100 bits at random. Remember that we're sharing a key that doesn't have to be any particular message. It just has to be some big number. And Alice sends 100 bits at random to Bob. And she's going to apply Hadamard to some of them at random. So what you've got on this slide is Alice makes up a whole bunch of random 0s and 1s. She starts sending them along the line, and at random, she applies Hadamard to them. She doesn't tell anyone for any particular bit whether she applied Hadamard or not. Why in the world would she do that? Bob, at his end, applies Hadamard at random to read the bits. Now remember that whenever they both applied Hadamard or both didn't apply Hadamard, Bob should get an accurate reading of Alice's bits. Well, what does that mean? That means that Alice started by sending 100 bits. Bob probably was able to interpret about half of them accurately. I'll tell you what, let's throw away the ones that we should not have read accurately. Why don't we do that? Alice and Bob, let's compare when we Hadamarded and when we didn't. In public, we'll publish it on the billboard in Times Square. Alice says, I didn't Hadamard for my initial bit, I did for the next 3 bits. Bob said, I did Hadamard for my initial bit, I didn't for the next 2 bits, and then I did for the next bit. Alice and Bob look at all this, and roughly half the time they agreed on whether they Hadamarded or not, and half the time they didn't. Well, when they didn't agree,
It help?
what? When they didn't agree, there's no hope. Let's throw away those bits. So here we go. They'll publicly share their decisions about when they Hadamarded. And whoa, what a strange, okay. Let me just tell you how to interpret this. The green arrows are for when they agreed. The red arrows are for when they didn't agree. And you see that little megaphone icon at the very far right of the slide? That means, hey, I can publish this information publicly. I can just announce when I Hadamarded and when I didn't. It's not harmful to do so. So the equal signs at the bottom here are when there's a green arrow. It's when they decided that they agreed. Now, so far, Alice hasn't published any of the bits that she started with, and Bob hasn't published any of the bits that he ended up with. All they've published is, all they've made public, and they didn't make it public because they needed to make it public. They just made it public because it didn't hurt. All they've made public is when should they be agreeing. Of those 100 bits that were transmitted from Alice to Bob, which half of them should they be in agreement on? And by the way, you can ignore a lot of the detail here. Just think about half of them you're going to agree on, about half of them they won't. Well, the quantum world works as follows. If there's an eavesdropper in the middle, there's absolutely no way for Eve to read a transmission without destroying it. You cannot read a qubit and make a copy of it and send it faithfully on its way. It's a quantum mechanical truth. To read is to destroy. So if there was an eavesdropper in the middle of this operation who was listening in on this communication, if she was listening in, then she could not possibly have faithfully forwarded the information that she got from Alice to Bob. That's just a quantum mechanical truth. You don't even need to know physics in order to know that. I have a slide where I do a little bit of math and just show it. It's just, wow, it's mind-blowing how simple it is. But the idea is there's this thing called no cloning. If Eve reads the message, then it's not going to get to Bob faithfully. Bob may read something, but he won't be able to read accurately what Alice sent. Well, what that means is that those 50 bits that we hope Alice and Bob share faithfully better turn out to be shared faithfully. I mean, after all, either Alice had a marted and Bob had a marted, so they should both have the same bit, or Alice didn't have a marred and Bob didn't have a marred, so they should both have the same bit. And that's going to turn out about half the time, and we know which half of the time it's going to be, wherever there's a green line and an equal sign at the bottom. So we've got 50 bits now that Alice and Bob better have in common, better be the same. If Eve was in the middle, then those 50 bits aren't going to be the same because Eve cannot read the bits, eavesdrop on it, and transmit them to Bob faithfully. So what do we do about this?
Can I ask you a question real quick?
Yeah, sure.
So why can't you send the whole key to Alice outright? And if an eavesdropper got it, then there's no way that a test message would verify. Like, why go through these games if an eavesdropper reading things would destroy it?
How can I tell that it was read? Or how can I tell?
Because what Alice actually receives turns out to not work.
Okay.
And you send a test message and she clearly has the wrong key.
So remember, it's okay that you're saying Alice receives something, but let's twist the terminology. It's Bob who is the receiver of messages.
Sorry. Okay.
Right? Okay. It doesn't make any theoretical difference. It's just easier to keep my mind.
You would think as a Bob, I would keep that straight. But
okay. Bob, you're the receiver. Alice sends an entire key to Bob, and then Alice sends a test message, right? How do they know that first of all, they have to have some way of coordinating and making sure that they both have the same key. Remember that this key is a random number. It's a big random number. So Bob has to have some way of verifying that it's correct. And since it's a random number, that's going to be hard to do, unless they share it publicly. Okay. Then Alice sends a message to Bob to test it. Now, again, they have to agree ahead of time what that message is. And if they have to agree ahead of time, then an interloper can read the message and spoof it.
okay.
Okay?
You said that by modding some of the bits, then they can tell that the message was eavesdropped on by the fact that the bits they should agree on don't come through correctly.
Yeah, now remember, it's not a message right now. They're exchanging random bits that were generated randomly.
Okay, but why do you need to mod them at all? Why can't you just say I'm sending the random bits, and if you don't receive all of them correctly, then someone was eavesdropping?
How is Bob going to know that he received them correctly or not?
How does doing the modding change his ability to know that he received them correctly?
All right, let's continue. Remember that we now have some green lines here. And the green lines, publicly, the world can know that the 4th bit had to be sent correctly. they have to agree on the 4th bit. And they have to agree on the 5th bit and the 6th bit and the 7th bit, but not on the 8th bit. I'm reading the bottom line of the slide. So they didn't agree Hadamard-wise on the 1st bit, the 2nd bit, the 3rd bit, but they did on the 4th, 5th, 6th, and 6th, 4th, 6th, yeah, 4th, 5th, 6th, and 7th bits. And as a matter of fact, they have a whole list of bits that they should agree on. And if there's an eavesdropper, agreement is not going to work because the eavesdropper cannot faithfully send these bits forward to Bob. Okay, so what do? They take half of those bits and they sacrifice them. They take half of those bits and they publicly, and notice the little horn on the right side there, they publicly say, we were supposed to agree on all 50 bits. Did we agree on half of them? Those bits are public now. We can't use them as the key. But we can check and see if those bits that Bob got that should have been the same as Alice's are the same as Alice's. And if they are, we know for sure that there was no eavesdropper. If there was an eavesdropper, the probability of all those bits being the same is almost 0. It depends on how many bits we started with. Instead of 100, we can start with 1,000. But the point is that by comparing in public Bob's bits that he should have agreed on with Alice's bits, then we can know either, yes, they're all the same and there was no eavesdropper, or no, they're not the same, there was an eavesdropper. And believe me, it's not going to be a one-off thing, or, it's going to be either, yes, they're all the same, or they're just half of them are the same, or something crazy like that. There's a clear distinction here between, yes, they agree, and no, they don't agree. Well, we've just sacrificed 25 bits to the encryption gods. We compared them in public, and we can't use them anymore. They've been public. They've been publicized. But look, we started off with 100 bits. We eliminated 50 of them because we know that they didn't have to be an agreement between Bob and Alice. We just shared publicly 25 of those 50 just to see if Bob and Alice did the same readings when they were supposed to do the same readings. But now we have 25 left. If it turned out that there was no eavesdropper and that Bob and Alice agreed when they should have agreed with those 25 bits, there's another 25 bits left that Bob and Alice both know that they haven't shared in public. So we can use those 25 bits as our private encryption key. Alice can take whatever number she has for those 25 bits, multiply her message by that number. Bob also has those 25 bits. He can divide the message by that number. They didn't really exchange these bits in any public way. Private, private, private key encryption. It all works, and it's, I must say, extremely clever. It's called the BB84 quantum key distribution scheme because people whose initials are BB, not Barry Bird, but something else, created it, and they did it in 1984.
Barry, I still don't understand what the Hadamard is, what benefit the using Hadamard is adding. Let's say you just sent the 100 bits without applying any Hadamard. Then you would publicly share 50 of those bits and say, do we agree? If there was an eavesdropper, they won't agree. If there was no eavesdropper, they will agree, and you can use the other 50 bits that weren't shared publicly.
If you're just sharing plain old bits, then they can be cloned. If you just take 100 bits and send them over a wire, and they're just plain old bits, not quantum things, not qubits, then it's possible theoretically for Alice to read them and copy them and send them forward to Bob.
Couldn't you send them as qubits without applying the Hadamard?
Well, Hadamard, if you send a qubit that's in the regular 0 state or the regular 1 state, then Alice can clone it, even though you call it a qubit.
Okay, got it.
Yeah, the Hadamard is to put it in this weird superposition state.
Since this is serial transmission, could both the sender and the receiver just have a 1 qubit device in order to make this happen?
Yeah, I don't see why not. Am I missing something? Could that possibly be a problem here? I mean, it would, assuming.
Well, I think about how they talk about how many qubits you need to do practical computing, but for this simple process of encryption, it would seem you could just have 1 qubit on either end and just sequentially do the same thing 100 times. It could be a very simple, very simple machine.
Now, in practice, it's more than 100. And in practice, they continue doing this during the sending of various messages. So, I mean, there's a lot going on here, but we don't need a pipe that can take 100 qubits at once to do this. And that's one of the reasons why quantum key distribution is a reality today. Whereas managing 100 qubits to do computations, to solve problems, to factor numbers is still beyond our present horizon. It's been estimated that to do real quantum computing where you're using it the way we use these computers to solve those kinds of problems, it's been estimated that it would take about 10,000 qubits at once. And we can only manage about 100 qubits at once right now. So we got a long way to go yet. Carl, did that address your question?
I think I understand this. I mean, like I say, I think you could have, in theory, 1 qubit on either end. It's a very simple machine that could do this kind of encryption.
Right, and of course, understanding that you have to serially send many qubits one after another to make this happen. Yeah. And I had something else brilliant to say about this a few minutes ago, but I can't remember what it was. Corey, are you still there? Did I portray this information accurately? Corey isn't answering. Okay.
She's in the chat. She says yes.
Oh, good. Okay. All right. Yeah, I'm
Yeah, I'm just not on video, that's all. I think it's pretty accurate. The only comment I guess I would make is, as far as can you do this serially with 1 qubit?
Yeah.
The issue is that the moment that you measure a qubit, the state collapses.
Right.
So it's decoherence, and then you won't be able to measure that qubit again with entanglement on the other qubit.
Right. But if you send 1 qubit at a time instead of sending 100 qubits at a time, then you can pull this off. There's not any requirement here that all 100 of these qubits be sent at once. You can send them like, take a couple milliseconds to send one and then another and then another and then another. There's
I
nothing, yeah.
suppose you could do that, but you would have to consider the act of sending a qubit. So how would you transmit it? If it's a photon, then I guess you could transmit it at the speed of light.
Yeah.
Doing 1 qubit, you might
Yeah.
have to retransmit every single time.
Right, no, you're not going to take the same qubit and transmit it 100 times. Is that instead of having a line that's 100 qubits thick and sending 100 qubits at once, you're going to 100 times generate a qubit, maybe Hadamard it, maybe have Bob Hadamard it, have Bob read it, and then you're going to do that with a second qubit, and you'll essentially get this entire spread. You just won't do it in a thick 100 qubit line. You'll do it one after another, but you have to do many of them, and they're going to be different qubits. Am I missing something?
Yeah, I'm not really the expert on the physicality part of this, the quantum mechanics portion of that.
Okay.
I have a feeling that it's not possible, that I have a feeling it's not optimal to do it that way.
Oh, definitely not. And as far as the physicality of it, my mind is up in the clouds here. So
Yeah.
I don't know squat about the physicality of this. So yeah, maybe that's more difficult than sending them 100 at a time.
I think so. The other thing to keep in mind is that you're creating a quantum system when you send multiple qubits,
Yeah.
as opposed to 1 qubit at a time. And I have a feeling if you're sending it 1 at a time that you're breaking the system because of that measurement rule, that once you do measure it, it collapses the state. And the act of transmitting that qubit, I think you'd probably be better off with using a batch of qubits, just like you would on a regular computer to transfer an ASCII message.
Okay, I'm not sure that I understand why 1 at a time would be problematic that way, but we'll look into it. We can.
I agree. I'm not sure either. I would have to look into that as well.
Yeah, cool. Okay. Well, I think we're near or at the end of this, and I'm proud of myself because the last 10 times that I explained this to people, they seemed to not understand, but I've got some, good nods and responses this time. So maybe I finally learned how to describe this stuff. That's really cool, and that's good. Are there any other questions, comments, discussion, anything you've got to say before we go? All right, I'm going to type my email address in the chat, and here we go. To everyone, my email address is barry@bird.org. There it is. If you have further questions or want to discuss this in more detail, then send me an email message, and be sure to identify yourself as someone who was in this discussion so I know to take the email seriously. And in the meantime, I thank you for coming to this talk. Hope you come to other talks in the TCF sequence, and we'll see you soon.
Thank you.
Hey, thank you, Barry, for the presentation. That
Thank
was
you.
interesting.